Okay, so in this example, we have wet steam. And what I mean by wet steam is that steam is a mist and it's composed of saturated water, vapor, and liquid droplets. And the quality of the wet steam is defined as the fraction of the mixture by mass that is vapor. So we have a wet stream at 5 bar with a quality of 0.85, and it's being isothermically dried by evaporating the entrained liquid. And we know the flow rate of the dried stream, which is all vapor. So first, let's draw out our process. So we have an inlet stream here. At some rate of kilograms per hour. And so when it comes to the composition of this stream, phase-wise, it's 85% vapor and 15% liquid. So that's we were able to get that from the quality. And we know that this is 5 bar and it is saturated. And we don't know the temperature. And then we know coming out of this process, out of the drying process, we have the same flow rate in terms of kilograms per hour. And we know the volumetric flow rate of this vapor stream is 52.5 cubic meters per hour. And we know that it is also 5 bar, and we don't know the temperature. So for part A, we are asked to use the steam tables to determine the temperature at which this operation occurs, also use it to get the specific enthalpies of the wet and dry streams, and to get the total mass flow rate of the process stream. So this is all coming from table B6, specifically page 646 in your book. And I'm looking at the column, which the column all the way to the left has pressure. So we're looking for 5 bar, and we're get all these values from that row that has 5 bar. So we were able to get that the temperature at which this is occurring, corresponding to 5 bar, is 151.8 degrees Celsius. And then we're also asked to get the specific enthalpies of the wet and dry streams. So the specific enthalpy of the liquid stream is 52.5 meters. Oh, sorry. It is not 52.5. That's 52.5. So the specific enthalpy of the liquid stream is 640.1 kilojoules per kilogram. And then also right next to it, the specific enthalpy of the vapor stream at this temperature and 5 bar pressure is 2,747.5 kilojoules per kilogram. And then we also want to know the total mass flow rate of the process stream. So we can get the mass flow rate of the process stream, so we know the volumetric flow rate, and what we need to get the mass flow rate is the specific volume. So the specific volume of at 5 bar and saturated steam is 0.375 cubic meters per kilogram. So to get the mass flow rate, we multiply the volumetric flow rate, which is 52.5 cubic meters per hour, times, divided by the specific volume, which is 0.375 cubic meters per kilogram. So 52.5 over 0.375 gives us 140 kilograms per hour. So that's it for part A. Now for part B, we want to calculate the heat input required for the evaporation process. So now that we know the mass flow rate and we know the phase composition of the inlet stream, we know exactly how much liquid is entering the process, and since we know that mass flow rate, we can also calculate the energy needed to vaporize that specific amount of liquid water. So the H2O evaporated is going to equal the mass amount of liquid that we have coming into the process. So that is our total mass flow rate of 140 kilograms per hour times 0.15, which is how much is liquid. So we are evaporating 21 grams of liquid per hour. So our energy balance, Q is equal to delta H. So what we'll need to do here is, so Q is going to equal to M times H out minus H in. So that is going to equal 21 kilograms per hour times 2747.5 kilojoules per kilogram minus 640.1 kilojoules per kilogram. Times 1 hour has 3,600 seconds, and there's 1 kilowatt per kilojoule per second. We end up getting that it requires 12 kilowatts of energy in order to vaporize the amount of water needed to vaporize the full amount of liquid water entering the process.